Hello everyone. In this video we will see how we can draw SFD, shear force diagram and bending moment diagram for the beam which is subjected to UVL, uniformly varying load. Uniformly varying load means at this extreme end, at end A, the load is 0, the load intensity is 0, and as you go to the right side at point B, the load is maximum. It is 20 kilonewton per meter. So it is uniformly, it is increasing. Okay, so there is a linear increase in the load with respect to the span. Okay. And the students, they find it difficult to understand the SFD diagram and the BMD diagram for a beam which is subjected to UVL, and we will see how to draw the SFD and BMD for this particular case. So the very first step is to find the reaction. I will define the reaction at A, RA, and reaction at B, RB. It is a simply supported beam. There will not be any horizontal reaction. Okay, so only vertical reaction will be there. And I want to find this RA. So to find RA, I will be taking moment with respect to B and equate it to 0, because it is a simply support. The bending moment, the resisting bending moment will be 0. So RA into 9. Okay, take all the forces into consideration to find bending moment at B and equate it to 0. Okay, RA into 9, it's a clockwise positive. RA into perpendicular distance is 9 minus, then you have the UVL. Okay, so we need to see where the total load of the UVL is acting. It will be acting at the centroid of the section of the area, center of the area, and you see it is just like a triangle. The loading, the arrangement of the loading is just like a triangle, and the centroid will be here. The distance of the centroid from B is 1/3 of 9 meter, and from this side it is 2/3 of 9 meter. Okay, so this is the centroidal distance, 1/3 into 9, and the total load is the area of the loading diagram. Area of the loading diagram means it's a triangular, so half into 20 into 9, and you see this is downward, and we are calculating bending moment with respect to point B. Okay, so this load will create anti-clockwise moment with respect to point B, and this is the perpendicular distance, 1/3 into 9 minus half into 20 into 9 into 1/3 into 9. This is the load and this is the perpendicular distance. Okay, so you don't have any load other than this. So RA, you will be getting RA equal to 30 kilonewton. To find RB, we have to use summation of f of y equal to 0. All the forces in vertical directions are added and equated to 0. Okay, so 30 is going upward. 30 is going upward. Plus 30 minus the forces which are going upward shall be taken as positive, and the forces which are going downward shall be taken as negative. And the UVL, the total load of the UVL is going downward. So minus half into 20 into 9. Okay, plus RB. RB, we have assumed that it is going upward, equal to 0. So RB equal to 60 kilonewton. Okay, you see the nature of SFD, shear force diagram, is parabolic, and nature of bending moment diagram is cubic. When the simply supported beam is subjected to UVL, and we need to understand how to draw the parabolic diagram of SFD. You see, this is a figure, and the SFD diagram, it could be like this. This is the parabolic distribution of SFD, and it could be like this. So both are correct, both are parabolic. Okay, so the only difference is in this is the slope. Here the slope is very less and here the slope is very high. So here the slope is very near to 0 or equal to 0. Here the slope is not equal to 0, it is very high as compared to this point, and at this point at B the slope is very high and here the slope is very near to 0. Okay, so we need to see which diagram is correct, which diagram we need to draw for this arrangement. Okay, so we know the relation of the slope and bending moment, of the shear force and bending moment, and also we know the relation of shear force and intensity of load. Okay, so you see slope of shear force is equal to intensity of load. Okay, so you see this is the SFD diagram, shear force diagram, and whatever the slope we will determine, it will be called as slope of shear force diagram. And you see the slope of shear force diagram is equal to intensity of load. At A the load intensity is 0, is very near to 0. Okay, then the slope of shear force diagram will also be 0 because the intensity is 0. And you see at B the intensity of load is very high, hence the slope of shear force diagram will also be very high. So we cannot take this diagram. This diagram says that the slope at A is very high, but what we have seen, the slope at A is 0 because the intensity of the load is 0, and in this diagram, which we cannot take, says that the slope at B is 0, but we have seen that the loading intensity at B is very high. So this diagram is right. We have to draw this diagram. At A the slope is very less, nearly equal to 0. At B the slope is very high. We can draw the SFD diagram, shear force diagram. Before that we need to calculate the shear forces at the point. So we have the step shear force calculation. Okay, so we have to see the point at the left of the point and at the right of the point. Okay, so in order to calculate the shear force, we will be traveling from left to right. Means we will be traveling from A to B. Okay, so in this way we will travel. Now first point is A, shear force at left of A equal to, you see this is the point. At the left of the point there is no load. Left of point A there is no load. Okay, so shear force is equal to 0. Shear force at right of A. So you are traveling from left of A to right of A, and one force is going upward. When you are traveling from left of A to right of A, one force is going upward, that is 30 kilonewton. So whenever you are traveling from left to right, the forces which is going upward shall be taken as positive and the forces which is going downward shall be taken as negative. As simple as it is. Okay, so one force is going upward, 30 kilonewton. And you take the next point is point B. Okay, shear force at left of point B, left of B. So we have to take this 30. Okay, so we are traveling from right of A to left of B. Right of A we have taken the value 30 kilonewton, right of A to the left of B. You see, when you are traveling from right of A to the left of B, the entire UVL is going downward. The total load of the UVL which is going downward. So the shear force will be 30 minus half into 20 into 9. So this is equal to minus 60 kilonewton. Okay, minus 60 kilonewton at left of B. Next point we have shear force at right of B. Right of B. Okay, so you take this point, you are traveling from left of B to right of B. So at left of B you take the shear force minus 60. So when you are traveling from left of B to right of B, RB is going upward. RB we have calculated RB, which is 60 kilonewton. Okay, so plus 60 will come here, which will be equal to 0. So now you can draw the shear force diagram. I will draw here. Okay, so this is the correct shear force diagram which we have seen. Okay, so at left of A 0. Okay, at right of A 30 kilonewton. Okay, at left of B it is minus 60 kilonewton. So if you are noting below the datum, you don't have to show negative sign. Above the datum positive, below the datum negative. Okay, so join this, it will be like this. We have seen that. Okay, at right of B it is 0. So plus minus, this is the SFD diagram. Okay, and this point is called point of zero shear, which we don't know. We have to find the point of zero shear, because we say that at a point of zero shear the bending moment is maximum. Okay, so in order to find the maximum bending moment, we should know the distance of point of zero shear. Now we will see how to find the distance of point of zero shear. So we will see how to find the x distance. Okay, so I will take this here. So this is the x distance. Okay, so I say that this point, I will define this point as C, and C is the point of zero shear. Okay, so I want to find this x distance. Okay, so we say that shear force at C is equal to 0, because it is the point of zero shear. And we also have to find this height. This height, it could be in terms of this is h equal to x into 20 by 9. Okay, so you know how to calculate that. I will draw here. This is 20 and this is h, this is x. By the concept of similar triangle, we can determine h in terms of x. So this is 9. 20 by 9 equal to h by x, h equal to 20 by 9 into x. Okay. So this is the intensity of the load at C, h equal to x into 20 by 9, and this distance is x. Okay, so we need to see what is the shear force at this point C. So we will travel from A to C. Okay, 30 is going upward, 30, and this UVL which is having width x and height h is going downward. So total load of it will be acting at this point, and total load is area of that UVL, this UVL, half into x into h. Okay, so minus, because it is going downward, half into x into h equal to 0. All the forces we need to consider between A and C. We don't have to go beyond C. Okay, so between A you have the between A and C you have RA, and you have this portion of UVL. Only this portion of UVL you need to consider, which is having x width and height small h. Okay, so this is the equation. 30 minus half into x. H can be written in terms of x. 20 by 9 into x equal to 0. So when you solve this equation, x will be equal to 5.19 meter and h will be equal to 11.53 kilonewton per meter, because it is the intensity of the load. We can draw bending moment diagram. Before that, we have to calculate bending moment calculation. You see, we have the 3 point. We have 3 point A, C and B. A and B are simply supported. So bending moment at A and bending moment at B is 0. Bending moment at A and B is equal to 0 because they are simply supported. They will not resist the bending moment. Okay. The only point we have where we can calculate bending moment is the point of zero shear, the C. At C we have to calculate the bending moment. Okay. So bending moment at C equal to, you see, you have to travel, you need to take only one end. Okay. Either you can travel from B to C or from A to C. Okay. So when you travel from B to C, it will be complex because you need to divide this UVL. So you will be getting UDL and UVL. So this is complex and this is not easy as compared to when you go from A to C, because you are only having the triangle, you are not having the trapezium. Here you are having the trapezium. So go from A to C in order to calculate the bending moment at C. Okay. So RA into X we have found out 5.19, 30 into 5.19. Then you have this portion of UVL. We know X, we know H, okay, and it is acting at the centroid of this portion. Okay. So this distance will be X by 3, 1 by 3 into X, you know that. Okay. So bending moment at this point will be total load of this UVL into perpendicular distance. So half into X is 5.19 into H we have calculated 11.53 into X by 3, 5.19 divided by 3. Okay. So bending moment at C is equal to 103.93 kilonewton meter. So now we can draw the bending moment diagram. Bending moment diagram: at A it is 0, at C it is 103.93 and at B it is 0. Okay. So C distance is at a distance 5.19 from A, and this distance you can calculate 9 minus 5.19. Okay. And the nature of the bending moment diagram is cubic, positive, BMD. Thank you for watching this video. Thank you very much.